Hi everyone. So in this video, I want to walk through why we need the x equals change x pattern for the add method for a binary search tree. So as a reminder, this is going to be that first version of the program I wrote on Wednesday, where we talked about the idea of the algorithm. Start at the top of the tree and go down, going left and right, depending on if the value we're trying to insert is less than or greater than the value at each node in the tree. If it's less than, we go left. If it's greater than, we go right. And then our base case was once we had an empty tree, we know we found the spot to insert this new node. So we said root equals new tree node. And this is the version I told you, is not going to end up working. So this version doesn't work because it doesn't change the tree. So let's walk through, and I actually set a little breakpoint in this search tree client so we can debug what's happening. So I've changed the constructor to build up a tree already to start with, and then we're going to debug what happens when I add a new number. So I'm going to add the number 65 to this tree. And let's go inside. And then I'm going to drag out our tree object. So you can see here I have this binary search tree already built up, but I want to add the number 65 to this tree. So our add method starts with overall root here in this public method, and then we say, okay, call this private add method passing an overall root and value. So root starts at 55. Because we're adding the number 65, we go into the second base case where value is greater than root.data, and we recurse right. So add root.right value. So this is a new recursive call, a new root variable. Fortunately, JGraphs only shows the root variable in the current method call. So this makes a new method call with a new root variable that's referring to the 87. And then in this method call, we decide to go left because 55 is less than root.data. So we end up going into this first else if, recurse on root.left. Then we're at this node. We don't hit our base case yet because root is not null. We're trying to add the number 65, which is greater than 60, so we go into the second else if. We don't go into the first one, we go into the second one and add that. And then in this last method call, root is now null because root.right in the previous method call was null. So now we recursed on root.right, that value is null, so we have null in our root. Now that root's null, we make a new int tree node, so that makes a new node with the number 65 in it. But then we don't do anything with that node with this first version. So at the end of this method, when we exit, we end up just getting rid of that variable. And nothing's there anymore because we never returned that new node out. It got lost. So just like that point example we saw, if we want to get a value out of the method, we have to return it. So as a reminder, the only two ways to change a tree is to either say .left, .right is equal to something, or to say overall root equals to something. Just like with linked list, you had to say front equals or .next equals. So the problem here is that we weren't modifying the tree. We just stored that new int tree node in a local variable. So the fix that we saw, let me end this debug real quick, was to use that x equals change x pattern. So the first thing we do is we return the new int tree node we just made. So I'm just going to say returns an int tree node, and I'm going to return whatever node I have right here. And the second part is every place we call this method, we want to actually go through and catch the return. Say something like overall root equals add of overall root. Oops, that's supposed to be an equal sign. Then root.left equals add of root.left. And root.right equals add of root.right. Because now this add method might return a new int tree node. So it might return this new node and we want to store a reference to that node in our tree. So we just need to add these things. And now if I go and debug the program, we'll get a slightly different picture. So I'm going to add the number 65 back in, step inside, drag out this tree so we can see it again. Let me make this a little bit bigger. Move it down here. Okay, so now that we have this tree, we can kind of go back in again. Okay, so overall root starting to point at the top node, and a lot of the logic is the same. Going down the tree, left and right, inserting this value 65. So first we go right, then we go left. At this point, we haven't done any assignments yet. We haven't done root.right equals because we're making a recursive call. We first have to evaluate the recursive call. So we make the recursive call, we go to the node with the 87, 65 is less than 87, so we go left. Then we get to the 60, 65 is greater than 60, so we go to the else if, the second else if, to the right. And then when we do this recursive call, we call add, and now on root.right was null in that context, so we're now in our base case. And so here we say, okay, set root equal to a new int tree node. So that's going to make a new node with the 65 like before. Let me make this a little bigger so we can see. And now when this method ends, we now do a new thing. We actually return this new root. So remember, when you return, or you have a variable of a type that's an object type, you have the reference. So returning root returns a reference to this new node with the 65. So when we do this return statement, we go back to the previous method call and return that value. Now, unfortunately, we can't quite see the return happening. This is kind of an intermediate step. We've just gotten back a reference to this new int tree node from that add call. And now we're saying root.write equals that new reference. So when I type this now, it now adds it to the tree. So this was a very important step. We return the new int tree node back, and then we say root.write equals that new tree node. And so that changes the tree. Now that we're done with this method, we kind of step down and return root. Root in this context, the node was 60. So we return root and go back to who called that. Well, that was a line that said root.left equals add of root.left in value. So we return that int tree node with the value 60 and set that equal to root.left. And root in this context is the node with the 87, as the arrow is pointing to here. Note, this is just going to set root.left to what it was before. That's okay. So actually, most of these assignments aren't really doing anything. It's really just in that last case where one of the roots was null, and that reference in root.left or root.right was null, and we return that new int tree node. But now this works perfectly. So hopefully this visualization makes sense or helps you understand why this pattern was necessary. But also, this is a great example to take the IPL if you're still a little confused on this, because it is a very complicated topic.